In this talk, I will talk about a unifying computational framework for teaching and active learning. This work is done jointly with Wei-King Wang, Yue Yu, and Patrick Shafto at Rutgers University, New York. In active learning, we have a world and a learner. The learner wants to learn how the world works, and he does so by actively intervening the world and observing the consequences. In teaching, we have a world, a learner, and a teacher. Here, the teacher helps the learner to learn about the world by telling him which intervention to try, or by directly telling him the consequences of particular interventions. The unification of active learning and teaching is based on the idea of self-teaching. Here, the learner imagines which intervention he would ask a learner to try if he were a teacher, and then he goes and tries out that intervention himself. Note that this imagination has elements of the theory of mind in it. Conceptually, this is pretty much it, very simple. Now let's go through some of the computational parts and give some substance to the idea. Shown here is a cycle of active learning. An active learner has a particular strategy to choose interventions. This strategy is described by P sub Lx, the learner's probability of choosing intervention X. The learner chooses an intervention X according to this strategy, observes the consequence Y from the world, and updates his belief about the world. If something concrete helps, imagine that the world can be one of these four hypotheses. As the learner makes intervention and observations, his belief about the world will update. Eventually, he will be fully certain which of the four hypotheses represents the world, which is denoted by H star. The apparent difference between teaching and active learning is that in teaching, the intervention and consequence are provided by the teacher instead of chosen and obtained by the learner himself. The process of teaching is depicted by this picture. The teaching strategy is described by P sub t, X and Y given H star, which is the teacher's probability of selecting intervention X and consequence Y to show the learner, given her knowledge of H star, the world. The teacher selects an intervention and consequence, shows them to the learner, and the learner updates his belief. Note that compare that to the active learning strategy, P sub L of X. The teacher's strategy, P sub T X, Y given H star, has the additional variables Y and H star. Both of these variables are related to the knowledge which the teacher has, but the learner does not. Thus, the unification will be about getting rid of the Y and H star. Mathematically, the process of teacher's selection and learner's inference are modeled by these two coupled equations. Note that these equations also have elements of the theory of mind. The learner's inference equation depends on reasoning about the teacher's selection, and the teacher's selection equation depends on the reasoning about the learner's inference. To help us remember the meaning of the terms, I have color-coded them. Red terms are related to the teacher, blue terms are related to the learner, and green terms, which will appear soon, are related to the world. The first step is to get rid of Y. We do so by marginalizing out or averaging out the probabilities of the different consequences Y. This is shown in P sub T X given H star, which is the teaching strategy after marginalizing out Y. Since Y is not given by the teacher, the learner is only shown the instruction to try intervention X. He then tries the intervention, observes the consequences Y, and updates his belief. In terms of the equations, the learner's inference equation now has an additional green term, which is the likelihood of observing Y from the world. This replaces the y, which used to be provided by the teacher in the red term. The teacher selection is simply the previous equation with y marginalized out. The next step is to get rid of H star. To do this, we first introduce the teacher's knowledgeability matrix on the left. This knowledgeability matrix says that if the truth about the world is a certain H, then the teacher knows that the world is that H with probability 1. This knowledgeability allows us to re-express the teacher selection equation with a marginalization over hypothesis G. And the identity knowledgeability, denoted by the delta function between H and G, will leave the teaching strategy unchanged. Now consider what a learner's knowledgeability matrix will look like. It will look like this one on the right. No matter what the truth about the world is, the learner's initial belief is that it can be any of the hypotheses. If we use the same marginalization operation with this knowledgeability, which is denoted by P sub L of G, then the resulting teacher selection becomes independent of H. Comparing this equation with the teacher's equation on the left, it is apparent that this is the case because the learner's knowledgeability is independent of H to begin with. Thus, by manipulating knowledgeability, we have created a teaching strategy that depends only on X. Note that this teaching strategy, P sub T of X, which depends on only X, is in every way a valid active learning strategy. To reiterate, this new active learning strategy is based on imagining a teacher who is only as knowledgeable as himself, or equivalently, imagining oneself as a teacher who selects interventions. So we call this strategy self-teaching. For completeness, the equations are shown here. The key points to take away are that the inference equation now recovers the normal form of Bayesian inference, and that the inference and selection equations are no longer coupled, as it should be in active learning. Now that we have a new way to do active learning, two natural questions follow. First, how is the self-teaching model different from the most common model of active learning, optimizing for expected information gain? Second, does the self-teaching model capture human active learning behavior? Let's answer the first question first. The first obvious difference is that mathematically, self-teaching involves only the rules of probability, whereas expected information gain involves the entropy function and subtraction, in addition to the rules of probability. The second difference is that the reasoning behind the models is different. Self-teaching is a metacognitive model that reasons about oneself's reasoning as a teacher, and this is captured by the red terms. In contrast, the expected information gain does not have this metacognitive element and reasons only about the interaction with the world, and that is captured by the green term, which is the posterior predictive distribution. The third difference is that expected information gain aims to reduce overall uncertainty, whereas self-teaching is more of a hypothesis testing method that aims to confirm relatively distinctive hypotheses. A distinctive hypothesis is one that is, on average, less likely to be inferred if all interventions and observations are equally likely to occur. Computationally, it is done in the following way. Here is the learner's posterior, the probability of inferring an H given a particular intervention X and observation Y. Darker color means higher probability. First, calculate a quantity called Z of G by summing over all the interventions and observations. A high value of Z of G means that G is more likely or easily to be inferred. The distinctiveness is then just the inverse of that. In this case, H2 and H3 are the most distinctive hypotheses. So the self-teaching tries to tell them apart by selecting to probe X2, where H2 and H3 are different. Now we come to the second question. Does the self-teaching model capture humans' active learning behavior? We will look at a couple of specific cases. For this boundary task, the task is to probe one of 3 locations to figure out which of the 4 hypotheses, H1 through H4, is the underlying hypothesis. Which probe would the models choose? For both self-teaching and expected information gain, we see that the center feature has the highest probability to be chosen. This is also what most people would do. Thus, in this case, the self-teaching model as well as expected information gain capture humans' active learning behavior. We now look at a slightly more interesting task called the causal graph learning task. In this task, you are given 2 possible causal graphs. The arrow indicates that if the upstream node of an arrow is intervened, the downstream node will show a reaction with high probability. The task is to figure out which of the 2 graphs is the underlying one by selecting a node to intervene. There are altogether 27 non-trivial pairings of these 3 node graphs up to rotation symmetry. We will look at a couple of examples. The 2 plots on the right are data taken from Coenen et al. And correspond to the 14th and 21st of the 27 pairings. A triangle is a simplex and represents the probability of choosing a particular node. For example, a point near the bottom left corner denotes that with high probability, the bottom left node was selected as the intervention. The blue cloud of points are humans' choices, and the red points are predictions from the expected information gain model. We can see that for problem 14, expected information gain is a good model of human behavior, but for problem 21, it is not. What does the self-teaching model predict? The plots on the left show the prediction of the self-teaching model, which are the blue squares, along with that of the expected information gain model and another model. As we can see, for problem 14, the self-teaching model is not a great model of human behavior, but for problem 21, it captures humans' choices very well. These 2 examples show that model goodness can vary from scenario to scenario. Nonetheless, it is encouraging to see that in some scenarios, the self-teaching model is a very good model of humans' active learning behavior, even when the popular model of expected information gain is not. Also note that I have chosen 2 examples where the self-teaching model and expected information gain give different predictions, but actually they often give very similar predictions, and these are often similar to humans' choices as well. In conclusion, we derived a self-teaching model, a novel form of active learning. This model depends on only the rules of probability, which may have implications for active machine learning. The model unifies teaching and active learning under a single learning mechanism, and it matches humans' active learning behavior in many scenarios. These are my collaborators, Wei-King Wang, Yue Yu, and Patrick Shafto. The talk is based on this reference. Thank you for listening.